FORGENIUS project is a EC-funded program under the Horizon 2020 framework program, and it is devoted to the characterization and description of the properties of the network of conservation of phylogenetic resources in Europe, from the point of view of a multidisciplinary approach, including genetics, ecology, modeling, ecophysiology, and so on and so forth, and that will produce a newly created information system. The program of today is, as usual in this type of webinars, there will be a speaker from within the project, Nicolas Martin, and then an invited speaker, Ciais. And so I think without any further delay, I'll leave the floor to Nicolas, and then Nicolas will present results from the project, and then he gives the floor and introduces and gives the floor to our invited speaker. Thanks a lot for coming, and it's up to you.
Thank you, Ivan. So I will share my screen. So can you see my screen?
Yep.
Yep. So yes, so I will present some work from the project actually, and that we conducted with Arsène Druel. For many of you, I guess you already see this work. You saw this work before. It's about something that we are doing for a couple of years. We are trying to assess forest drought-induced mortality risk using plant hydraulic modeling. And here we will present something we developed in FORGENIUS, which is a self-calibrated algorithm to maybe try to be more accurate in predicting the risk of drought-induced mortality in forest. Many colleagues are, of course, involved in addition to INRAE, obviously, colleagues from the project and from other projects. So, as you know already this, so forests are undergoing strong climate change effects, and we observe mortality in different places of the world, such as here in spruce mortality. In France following 2018 drought, so it's drought plus bark beetles, but still triggered by drought, and we have a lot of this example of mortality worldwide. And these desiccation events of plants during drought are related to wildfires as well, and other disturbances such as wildfires. So what do we know about the physiology of drought-induced mortality? So to make a long story short, we had this framework from McDowell that drought-induced mortality can be related to two main aspects of physiology. On the one hand, you have the carbon starvation effect, which is related to the fact that during drought, plants close their stomata, and so they reduce photosynthesis and available non-structural carbohydrates for growth and survival. And on the other hand, you have this hydraulic failure effect, which is that very deep drought can lead to the embolism in the vascular system of the plant, in the xylem of the plant. So here you can see xylem conduits of oak, which are full of water, so you cannot see any dark gray area, but here it's completely embolized, and you can see dark gray area in the vascular system of this oak, and it's then desiccate because of the drought. And you can also observe this kind of air bubbles in leaf as well when it's very dry. So since this framework from 2008, a lot of measurements have been conducted in the field, and like a few years ago, this meta-analysis came out and shows that in most of the case of drought-induced mortality in the field, hydraulic failure was involved and not always carbon starvation. So we now know that hydraulic failure is one of the main mechanisms involved in drought-induced mortality. So to predict this phenomenon, what we did is that We developed this model, which is called SURO, which is a plant hydraulic model, actually. There are others, but this one integrates a lot of the traits that we measured in the FORGENIUS project and elsewhere in the world. Actually, it's a process-based model that represents the plant and the soil plant atmospheric system as a series of resistance and different point in the plant, actually the stem and the canopy leaves. It models the transpiration and the water potential of the plant, and of course the risk of drought-induced embolism in the apoplasm, which is the xylem of the plant. So this model, SURO, accounts for climatic data like any hourly climatic data are needed, like temperature, vapor pressure deficit, rainfall, radiation, but also plant traits. And this is very important, that it integrates direct plant traits that are measured in the lab, such as vulnerability to embolism, the stomatal regulation that we can surrogate using the Turgor loss point, the cuticular conductance of the leaves, and the capacitance of the branch and leaves. And it also accounts stand properties such as the leaf area of the plant or the leaf area index of the stand, the plant size, which determines the water stocks actually of in the plant, and also, of course, the soil properties, which define the soil water capacity, the total soil water capacity that we call TAW. And with all these inputs and the model, you can compute the transpiration of the plant. So here it's like a theoretical dynamic when you put the climate constant and you remove the rain in the inputs, and you have a constant hourly climate every day. You have this transpiration pattern that reduces due to stomatal closure, and then you just have the minimal transpiration here. You model the water potential in the plant at the different level, but here it's in the leaf apoplasm, and the level of embolism that if there is no rain, increase up to hydraulic failure where the plant can die. So this is a theoretical simulation, but you can also use real climatic data and real plant trait data, and have here, for instance, it's a silver fir at the Canigou mountain in the Pyrenees, and during the year 2017, which was very dry, and you have 10%, a few percent of embolism. Well, so for this model, and we have most of the input data, actually. We have climatic with ERA5 length, for instance. You have this at global scale. Traits data can come from our measurement in the lab, but also from databases. Stand properties such as leaf area index or plant or canopy size can be estimated from satellites now using MODIS or Probavi. But we miss this parameter, which is, however, very sensitive, which is the soil water capacity, which related to texture, rooting depth, and stone content. This parameter actually is very important, but it's not visible from space. And so in this approach, what we did is that we use the model to calibrate these parameters. And we use an ecohydrological equilibrium hypothesis from Eagleson, 1982. We formalized this idea that the canopy, the leaf area of a forest, the leaf area index, is in equilibrium with the water supply from the climate and the soil in order to minimize water stress. So what we basically did is that we calibrated these parameters by simulating for a given climate, a given set of traits at any site, any forest site, and stand properties that we can get from satellites. We can model for the 30 past years, for instance, the dynamic of embolism for these conditions. So this is what is here in red. Using this, we can estimate what we call the hydraulic risk, which is the quantile 90 of the level of embolism for a given for this condition, and a first guess of soil water availability, total soil water availability, and and we can report this value of hydraulic risk on a plot, and we can repeat the operation by changing the value of the soil water capacity, for instance, by changing the stone content. And by doing so, we can have a curve like this one, which expresses the hydraulic risk as a function of this total soil available water. And then if we define a target risk above which the plant cannot go, for instance, we know in the field that the plant in general maintains a risk below 10, 20%, we can have an estimate of this theoretical total available water. And this is what we did to get this missing parameter and be able to estimate the missing parameter anywhere in any forest. So we try to evaluate this using ICOS forest sites data of eddy covariance fluxes, and we applied the approach I just described. Before applying it, we first evaluated the model using the eddy covariance value of evapotranspiration. This is the model evapotranspiration, and this is the measurements. So we have a quite good correlation. And we applied the algorithm. So we didn't use real field data because they are available of climate, species, or LAI. We took ERA 5 land climate. We took the species from a land use map, from the Köppen land use map. We estimated the species from the Köppen land use map, and we used leaf area index from the ProbaV Sentinel-3 satellite. And then, we estimated this value for the 15 sites presented here, and we compared with the value measured on site. And we found a quite fairly good correlation given the uncertainties we can have in any of this data. Then we evaluated the uncertainty related to the different inputs, in particular related to the species, to the soil texture and the LAI by setting constant either the species or the LAI or the texture. And this is what I present here. So you can see the value of TAW estimated with a constant soil texture for all the sites, or here the value estimated with the real soil texture extracted from here. It was from soil grid. So there is no effect on soil texture. Then we tested the same thing with the species trait. So we use a constant species for all the sites. We use Quercus robur, and you see that you have a deviation. So which means that there is a quite important sensitivity to the traits. But and we did the same exercise with the leaf area index by setting constant or not the leaf area index. And as you can see, there is a big drop here, which actually indicates that this approach is very sensitive to leaf area index and to a lower extent to species trait. So briefly, what we did then is that we applied this approach to a set of mortality data from Christian Piédalu on the Vosges mountain. It was a mortality event after the 2018 drought. So there are 2,000 sites. We extracted the soil texture data from soil grid. We use ERA 5 land data downscale for the different sites of the Vosges. We use LAI data from satellites. Yes, on these sites you have green dots which are living, and red which are sites where Christian Piédalu and the group observed mortality. And we applied the TOW algorithm, and we compare and we estimated the hydraulic risk during the 2018 drought using either the TOW algorithm that was self-calibrated, or using the SDAC database, which is the European database for soil. So as you can see here, when you use the TOW estimated from SDAC, given by the SDAC database, you cannot discriminate between sites with mortality or not. But when you use a TOW self-calibrated algorithm, you can discriminate significantly, some sites at least. So you have kind of improvement by using this algorithm if you want to estimate drought-induced mortality. So yeah, the next step, I will be short. We want to apply this on the different sites of the genetic conservation units of the project, for which we have many field data. We have the traits of the species, we have the texture measured on site. Here it's an example for Pinus pinaster. And we have LAI measurements, but as I told you before, so LAI is very sensitive in the algorithm, but we have different estimates here, which give different value actually. So we have here an issue. We need to try to stabilize LAI information, and we are going to use, at least for France, LiDAR data to try to consolidate leaf area index estimates, because we apply different methods in the project, and according to the method you have different value. This is what shows this plot. So each bar, for one GCU, each bar is a method. So we don't have all the method everywhere, but well, so the conclusion is that the Suro model can have a great potential to assess drought-induced risk on forest, and we can apply this algorithm maybe to constrain the model with a lot of data and estimate the data we need and we miss, like the tau. But we need some forcing data such as leaf area index, which are very sensitive but still quite uncertain. Thank you for your attention. I think I was a bit long, so maybe we can, because you know this already, I could introduce Philippe, and we can see the question at the end. And we
Sounds
start a
right.
bit late.
Yeah. Please go ahead. Thank you, Nicolas.
We are very happy to have Philippe Ciais with us today. I am not sure it's still necessary to introduce Philippe, but because, as you know, he's one of the most famous researchers in geoscience and environment. In a few words, Philippe is working is a physicist working at the Laboratory for Climate and Environmental Science close to Paris-Saclay. He has been working a lot on GES and global carbon cycles and the feedback between climate change and ecosystem functioning. He has contributed to the development of many atmospheric and land surface models, such as Orchidea, and he has been involved in the setup of the French ICOS, so greenhouse gas monitoring network, ICOS, and he is also working a lot with remote sensing and use them as tool to monitor ecosystem and GES emissions. So his speech will be on this, I guess. So Philippe, I leave you the floor.
Okay. Thank you very much for the introduction. I'll try sharing my screen. Hope it's okay. Can you see my screen now?
Yes.
Is it okay? Can you see my screen?
Yes.
Okay, because then I can't see you anymore. So I'll be happy to speak about how we can use remote sensing data from different sensors and artificial intelligence models to improve monitoring of forests. This is some work we do with colleagues from Denmark, Germany, also INRA in Bordeaux. No need to remind you that Europe and its citizens cherish the forest, in particular for their services related to water, biodiversity conservation, but also climate mitigation. More precisely, the European Commission and its member states have decided to include the land use sector in their neutrality objectives by 2050, and they agreed upon maintaining a carbon sink of 400 megatons CO2 per year in 2030 to partly offset industrial emissions. This is in the land use sector, but it's primarily about keeping a significant forest sink. Why are forests a large carbon sink in Europe? It's mainly because of demographic reasons. A lot of the forests have been clear-cut or rejuvenated just after the Second World War, in particular in Central and Eastern Europe. And since then, we have seen large-scale plantation or replantation or conservation programs. And in fact, since 1950, the total build-up of above-ground biomass carbon stock has been very large because the carbon stocks have been multiplied by 3 over the last 70 years. In the same time, the forests have been growing quite well because in the same time, like part of the increment has been used to increase the carbon stock density. We've been also taking out wood from the forest at a rate of about 150 million tons of round wood per year. Forests have expanded their carbon sink slightly because of area increase, but mostly because of higher trees and also denser stands with more trees inside each forest. However, since 10 years, we see a significant decline of the forest carbon sink. This is from the kind of official inventories based on the national forest inventories that are submitted by different governments to the UN. The green curves denote the kind of ecosystem level carbon sink, and the positive numbers are carbon sources from non-forest ecosystems. And as you can see, the European forest sink was close to the European target of 400 until 2010. And since then, we have had a number of extreme droughts in Central Europe in 2015, 18, 22. Followed by insect attacks related also to post-drought effects, and the European sink has been decreasing by almost 20% now. Mortality has increased, and it seems now to be extremely challenging for the European commitment because we are following a declining trajectory, which was not foreseen, I think. And the target of 400 that looks kind of easy to meet is now probably not going to be met, which means that there will be some important consequences for the European position in the international climate negotiations. Things can be even worse in some countries because mainly of bark beetles and droughts, like you can see here, the Czech Republic. Switch from sink negative to source positive here in established forests has been very rapid. The Czech Republic is now a net source of CO2. Finland is also a source. Germany is going to be a source. And this change has been very, very quick. Looking at the situation in France, we can see that France has also experienced a very sharp decline of its carbon sink from repeated inventory campaigns. It's about a decline by 50% in 10 years. And the French government is also providing additional data at national but at regional scale that help us to try to better attribute this declining sink, which is the kind of dark green curve in the middle, to gross losses and sinks. On the one hand, the kind of gross increment or the forest growth in light green has been decreasing over time after 2010, where it was increasing before. On the other hand, the harvest has been stable or slightly increasing. Of course, this is masking very large regional differences given the management intensity of forest. And the most worrisome thing is that the natural mortality from droughts and insects, which was very low compared to the harvest, has increased by about 80% in the last 10 years. In fact, natural mortality increased, and kind of failure of new plantation has also increased dramatically because now in France there is about more than 1 chance out of 2 for a new planted forest not to be able to survive. Do we have the right data to monitor those changes going on at scale? The answer is probably no. We have forest inventories. They are good because they provide long-term records. They have tree-level data. However, the sampling is not very large. In France, about 7,000 plots are remeasured and 7,000 are new measurement every year. If you have 100 departments, which are not tree units, it means that in one department, you rely on about 50 to 70 plots, no more, to calculate a change of carbon. And of course, it's very sensitive to the random sampling of the inventory. Furthermore, inventories have a revisit cycle of 5 years, which means that if you have a shock, like in 2022, we have a very bad year. In 2023, we start to see some plots that have been affected by the shock, but we will know more about it. It will be worse in 24, 25, 26. And basically in 28, we will know more or less what has been the impact of the shock, but it will be very late compared to the Paris commitment. And last but not least, I've been trying to access NFI plot level data with various success. Some countries are, providing data for research, others are blurring the coordinates, or they just answer. So the data are not easily available, and we hope this will change with the setup of European monitoring system. We have adequate flux towers. Of course, they are very good. They provide estimate of fluxes. They are very good for understanding processes, energy and carbon fluxes. However, it's very difficult to upscale data from those towers into a carbon stock change. So based on that, you can look into space observations. We do have a number of sensors that have been covering the entire globe, like MODIS, every day at 250 meters, Landsat with much less frequent images, but a higher resolution. We have radar and passive microwave observations, but I would like to make a case in the rest of the presentation for using high to very high resolution images. I'm talking about Sentinel data at 10 meters or even the planet data at 3 meters, which offer a new window for understanding forest carbon change. So satellites have good attributes. They offer a full spatial coverage and frequent revisit. With the planet constellation of data, we have one image of the globe every 3 meter resolution every day. So this is an incredible amount of data. However, as you probably know, there is no satellite that measures carbon, and even less that measure carbon change. So you need models and algorithms to transform satellite physical observations into carbon observations. That's what we've been doing. We've been basically operating the fusion of different sensors, radar, optical, microwaves, considering ground-based observations. And we've been using deep learning models to provide a global map of biomass and biomass change, very high resolution maps of forest height, structure, biomass change, and also digital map of tree cover at 3 meter scale, and even tree level carbon inventories. I'll just present some examples in the rest of the presentation. Yeah. So one first example of what we can do at global scale with Jean-Pierre Vigneron. He's been exploiting basically what was kind of noise for the retrieval of soil moisture from the SMOS satellite. It's an antenna that receives microwave, which are emitted by the land surface. And when there is more vegetation, there is more water in the vegetation, and you have more emissivity. And the vegetation optical depth index has one advantage over optical and radar, because it's a long microwave wavelength of about 20 centimeters, is that it shows very little saturation with biomass up until about 200 tons per hectare. So we use a reference calibration map between the VOD, the vegetation optical depths, and the biomass, and we have continuous measurements since 2010. So we were able in this paper published in Nature Geoscience to provide a global map of forest carbon change. Not surprisingly, you see in Siberia and Australia, big losses from fires, and in South America and the Congo basins, significant losses from deforestation activities. On the other hand, some regions, in particular in southwest Russia, north of the Congo basin, and in southern China, where you have a lot of young forest, have been significant carbon sinks. This data have been used to evaluate global models, and we found that most of the global models don't have demography, they don't have disturbances. So as a matter of fact, they tend to overestimate the carbon sink in biomass in tropical forest, where there is no limitation and a strong CO2 fertilization effect, whereas the reality tends to suggest that the largest carbon sinks on Earth are located in relatively young forests of the temperate and the boreal regions. Yet the VOD is nice. It's a long time series, but it has a very coarse resolution of 25 kilometers. In Europe, a 25 kilometer pixel can contain forest, but everything else. And that's the reason why we've been trying to develop high resolution maps. Using a new and interesting instrument called JEDI. JEDI has a series of lasers, and basically it's like a forest inventory. And JEDI is flying over the earth, and it's collecting measurements on footprint. A footprint has about 22 meters of diameter, the size of a classical NFI plot. And it's taking a measurement of the dominant height, but also of the full waveform, which is related to the vertical structure of the forest. So we have measurement of heights, thanks to JEDI, at least south of 52 degree north, but the measurements are sparse. We don't have them everywhere, and we wanted to develop maps from sparse measurements. So we've been using deep learning models, which are derived from medical imagery and computer vision. The game is that we have a few target data, like JEDI, I mean, it's an understatement. In France, we have 110 million of JEDI footprints. We give as an input of the model continuous images from multispectral data from Sentinel-2 and radar 4 bands from Sentinel-1 data. And we want to create a continuous map based on sparse JEDI labels. We use a UNet model. It's a convenient architecture because it's very flexible. Basically, it makes successive transformations of the original images up until you get a fit to the data, and then it backwards propagates the transformation of the images inside the neural network in order to kind of best regress the JEDI height data against optical and radar data. If you see it as a regression, although it's not a regression model, it learns from context, you have about 110 million of Y variables. You have about 17 million of regression coefficients, trainable weights for the UNet model, and you have about 1 billion of 10-meter pixels from Sentinel-1 and Sentinel-2. So we created maps of forest height at 10-meter resolution, because it doesn't make sense to do biomass at 10 meter because of the kind of between tree heterogeneity. We used a relatively simple allometric formulation to provide a map of biomass over France at 30-meter resolution. This is how the height map looks like. All the data are publicly available, and you can see that the forest in the Alps, Vosges, and the Pyrenees tend to have much taller trees than in the south of France or in plantations like in the Lelang region. So to summarize, this is a forest in the north of France. It's called Ciais. You have a Google Earth image on the left, and you have the JEDI data as they are. You see some structure. Yellow colors indicate high values, but you see that close to the high values, you have some low values of height or some medium values. It's very difficult to make an interpolation of this with human eyes. And this is what our model is providing. You discover that there is, of course, a very strong spatial structure related to the different forest parcels of different age. But even inside these tall forest parcels, you see some degradation features, even roads, and a lot of small-scale heterogeneity that were not discernible using the JEDI data alone. How good are these data? It's purely satellite-based, so of course it needs to be evaluated against independent data. So we performed evaluation with this ICP forest network called RENECO4. Also the National Forest Inventory plots. I don't have the coordinates, but they kind of made the comparison for me. It's all the green areas, and we have some airborne LiDAR campaigns. The results are shown here. On the left, you have the predicted height purely from JEDI and Sentinel, and on the x-axis, you have the NFI height that was not used as an input of the model. The right is the same plot, but for the airborne LiDAR campaign. As you can see, there is a quite high correlation between our satellite map of height and the ground observation, which are completely independent. Also, we tend to slightly underestimate the height of very tall trees. And the mean error is 3 meters for height for against the NFI data, which is better than any existing product. So indeed, we wanted to understand how this deep learning model compares with other products. We have 3 of them. One is made by the University of Maryland. It's based on the Landsat and JEDI data using a random forest. It's better by Potapov and his group. The second model is also using a UNet, but it's only using Sentinel-2, and it's also using JEDI to map height over the globe. And there is a new product based on the planet data trained against airborne LiDAR campaigns that provided a height map at 3 meters over Europe. Let's look at how the different maps compare with each other. So you have on the left our product called FORM-H. You have the planet data just to the right, then the Lang map and the Potapov map. Visual comparison suggests that the Potapov map is very uniform compared to the heterogeneity of our map. The Lang et al. Map has some similarities. Also, it has also large differences, for instance, in the difference area here. It's also a bit more fuzzy. And the Li et al. Has some contrast, but it does not capture very high biomass values or high height values in the central part of the forest. This is for visual inspection, but we can look at the comparison statistics with independent data. On the right, you can see that the Potapov map has absolutely no correlation with the true height from airborne LiDAR. The Lang et al. Map has a correlation of 0.3, the planet data of 0.36, and we have a higher performance. Why is our map better than other maps? Maybe because we have a better deep learning model architecture. Maybe because we are using Sentinel-1 radar data and not only optical data like Landsat or Sentinel-2. Maybe because we trained the model over France, so we have more experience, and the other maps were global. So I'll come back to this later. Once you have an accurate height and biomass map, you can use it for a number of applications. The first application that was published with colleagues from Montpellier has been to look at the biomass loss from the Sentinel-2 fire polygons during these extreme years of extreme fires in 2022. You can see on the bottom panel that usually burnt area occur in the Mediterranean forest and in Corsica, but in 22, there was a lot of extreme fires in the maritime pine forest of Leland, but also in temperate regions like in Brittany and in Jura in France. And we found that because of the highest density of biomass over those forests compared to the Mediterranean ones, although the burnt area was significant, we also have a kind of disproportionate biomass loss. So that's one of the first applications. You can look at the biomass loss during disturbances. The second thing is that you can also try to work out on the disturbances to have a better idea of what happens, because if we have a decline of the European carbon sink, it's probably reflecting a change in the disturbance regime. We have a nice map of disturbance from Landsat, from Cornelius Senf and his group, but this map is not attributed to agents. And what we wanted to do again with deep learning is to separate different disturbance polygons into storms, fire, harvest, biotic dieback like bark beetles, biotic mortality, and drought dieback. For that, we use an algorithm called dbScan, where we take a disturbance polygon and we look at proximity data. For instance, we have NFI data in a certain radius of the disturbance polygon. We have French data from the DFS, the National French Forest Service. It's more than 10,000 plots. We have a semantic database called DFDE from the European Forestry Institute. It just tells you, oh, there is a fire in the Porto Vecchio region of Corsica in 97, but this information is also usable. And we use also, I think, additional information from the global forest loss polygon. And based on that, by defining spatial and temporal probabilities of one polygon to be close to, here, for instance, you have an NFI plot observing some mortality from insect. Here you have another one with mortality from insect, and here you have like another type of mortality. So defining probabilities for a polygon to be something in space and in time, because the temporal location of the Landsat disturbance is not perfect, we're able to create this map in the middle based on the dbScan algorithm, which is basically clustering the disturbance polygon into causes. And you see that, not surprisingly, in France, most of these disturbances are harvest, but you have a couple of storms in Brittany, a couple of biotic dieback, mainly insects in yellow, biotic mortality like bark beetles in the east of France, and drought effects. So this is the first attempt to classify disturbance into different agents. Second application if you have a static height map, and if you know what was the disturbance associated to each height or each biomass, you can use a space for time approach over the Landsat era to derive what is called the biomass age curve, essentially a regrowth curve or height age curve after disturbances. This is the results for a small region in the center of France. The reconstruction of the height versus age, like a growth table, if you want, from Landsat is in color, and the NFI points are the black points. First of all, you see that the satellite-based regrowth curve has a very good agreement with the NFI data, and you have very different growth rate between Douglas fir, for instance, that grows very fast and very quick, and oaks and poplar and so on. So you're able to define growth rates as a function of time since disturbance for each type of species in a region. And because you have a lot of data, it's also possible to understand how those growth curves are spatially modulated by different factors. Of course, they depend on age, but we found also that the second factor that was controlling the growth rate of forest was the patch size of the previous disturbance, which was unexpected, probably because of seedling propagation. If you have a very large disturbance, it takes longer and the recovery is slower. The third effect was the species, as you can see visually on the curve, but also there is some soil properties like water holding capacity or pH that also determine the spatial distribution of the growth rate. Now that you have some growth rate, you can derive basically a regrowth curve for every region of Europe, provided that you take small landscapes. We took 18 by 18 kilometer regions. And we use three data sets. The first one is a reference map, not from us, from Ciais. It's a reference map of biomass for the period 2017-2020. In the middle, we have the disturbance map from Senf and Seidel, and on the right, we have the NFI data. First of all, you can see in the middle that if you look at the trend of disturbance, they are increasing everywhere and increasing in severity, except in the Mediterranean regions. So boreal, alpine, Atlantic, and continental regions, the big region you see in the little corner here, show an increase in the severity of disturbance. Then what we do is that we calculate for every very small region, like 18 by 18 kilometer, a regrowth curve, which gives us the carbon gains after a disturbance. And we calculate a loss from disturbance. But first of all, we wanted to verify against field data that our satellite-based recovery rate of biomass after disturbance was comparable with field data. So you see different rates of recovery. Of course, in boreal forest, the asymptote is lower than in continental regions, and the early growth rate is different. But the good news here at the bottom is that when you compare for different ages after disturbance on the x-axis, the difference between the satellite-based biomass age curve and the kind of chronosequence plot-based biomass age curve, there is a very little bias. There is quite a bit of noise, of course, but this suggests that the satellite can describe with a high accuracy the biomass gains after disturbance. So then what we did is that we built a model to try to reproduce the carbon trajectories of the European countries. The blue dots are the UNFCCC reports, basically the NFI. The black line is our model, which is completely independent of NFI almost. And as you can see, there is a very good agreement between our models. So basically, we calculate the biomass loss every time there is a disturbance and the follow-up biomass gain using our recovery curves. And we provide here aggregate results, but of course, the results are available on the map at 18 kilometers. The only parameter that we had to tune is the parameter concerning the ratio between disturbance severity, because in the Senf map, we only have severity index. We don't have percent of biomass loss, and the percent of biomass loss. So we adjusted this ratio per country against the NFI data. So our early value of the model is kind of tuned to NFI data, but then the trend is free running. And as you can see, the model is able to reproduce very well, just with satellite data, almost the observed trend of a declining carbon sink. On the other hand, if you take the Ciais map and you say, well, they are available from 2017 to 2020, why don't I take the difference between 2018 and 17, 19 and 18, and I will also have a carbon change. And you can see, this is the red dots, that the CCI map are always showing a carbon loss for European forests. And this is not possible. We have a carbon sink, it's going weaker and weaker, but we don't have a carbon loss in biomass. And when we looked at the data, we found that there is a lot of striping and banding in the CCI biomass map, which is due to the ALOS data. Maurizio Santoro, who is producing the map, is aware about this. And the take-home message is that making a year-on-year difference of the current satellite biomass map is not good enough to look at forest carbon change, but the maps are still good enough to derive growth curve and then to build a model. Once we have a model, we can extrapolate it to the future. So for each pixel, we have 35 years of Landsat disturbance. So we have a linear trend of the disturbance severity. And we very conservatively assumed that the severity of disturbance will continue at the same rate 10 years in the future to see what will be the carbon sink of European countries within 10 years. And then we let the regrowth curve that we have from current satellite data calculate the recovery from disturbance. So you have losses in pink and you have gains. So the growth is decreasing. The losses are increasing because of our extrapolation of the disturbance severity trend. And at the EU level, we can see that our model is predicting that we will have a continuous decline of the European forest carbon sink down to about 100 million tons of CO2. And the objective is shown here. It's about a bit less than 400 million because it's only for remaining forest. But our model suggests that even a conservative assumption with the current business as usual for disturbances will not take us at all on our commitment for the Paris Agreement. If you want to be more provocative, if we wanted to meet the target, basically we would need to reduce harvest, and we would need to reduce harvest of European forest by 43%. If we wanted to give a break to the forest, let them regrow and meet the climate targets. Now, some more result. Everything I have presented is basically based on a static map. We wanted to check and to see if it is possible to have a direct measurement of biomass or height change using the same kind of UNET technology. We have to be careful here because height change is a small order effect compared to absolute height values. And the model is then very sensitive to phenology. For instance, 1 year you train how to learn how to make a 30-meter height from a yellow forest because there is a drought. Another year you come over the same forest, it's very green, and you are going to learn how to make, a 30-meter height from a green forest. In that case, of course, the model can be fooled and can show spurious height changes just because of phenology and drought. So we managed to develop a kind of new architecture of the UNET model to make it resistant or agnostic to years and phenology. And the result looked like that. So we now have annual map at 10 meters of height, here from 2017 to 22, small regions of Leyland. The difference is shown on the right. You see red areas, which correspond to very strong height losses, and these are pretty obvious. You have some clear-cut forest in this region. You have maybe some thinning here or some degradation. But more interesting is the fact that you have a lot of parcels that show an increase of height. And we were wondering if this increase is just noise or fantasy from the remote sensing and the artificial intelligence model, or if it had something to see with the reality. So we sampled here 1 million of 10-meter pixels over the Leyland forest. We consider the height map in 2018 as a reference, and we plot the difference between our map of height in 2019 versus 2018, 2020, and so on. The x-axis is the height of every tree as it was in 2018. And we can see that 5-meter tall trees, young trees, are growing by 1 meter per year. That 15-meter tall trees are growing by half meter per year, and then very older trees in the Leyland forest, you don't have taller trees than 25 meters, are growing very slowly. So indeed, it seems that our model is quite good. It's quite robust to start monitoring year-on-year changes, and you see things that you would expect, like young trees are growing faster than tall trees. If you go to another species, like Aleppo pine in the Provence region, it's a very different story. The growth rate is very slow. It's a kind of slow-growing species, and most of the growth rate is concentrated at heights of larger than 10 meters. If you take, very fast-growing plantations like Douglas fir, Over central France, when the canopy closes after plantation, these are real monsters, you know, they grow by 1.5 meter per year, and then the growth kind of saturates. So you're able to determine directly from satellite data the year-on-year growth of trees in different regions. And we made here a map of the kind of mean height on the left and the mean height increment over 5 years from the Sentinel and Jedi data. Not surprisingly, young forests permanently harvested, like Leland forest, have the highest of all increment. This is studies over France, so we wondered if it's possible to do that for other regions. On the one hand, you have some global product, like the Lang map or the Potapov map. We made a map of France. We created map from Ghana, Tanzania, Spain, Italy, Congo, Amazon, and every time we find that there is a big quality difference between the regional map, which are better, and the global map. Now we have a continuous map of forest height over the entire Congo basin and over the Amazon, as well as Southeast Asia. We are very pleased to see that even though tropical forests are much more complex, you have much more clouds affecting the Sentinel-1 data, much higher biomass, taller trees, and so on. Our mean error for the same kind of unit model is only 5 meters. It's worse than in France, but it's not catastrophic. It's much better than existing data sets. And in collaboration with colleagues from Münster University, they have a lot of CPU, GPU. So we trained a global model. It's about 45 terabytes of input data, 2 gigabytes of labels, target data from Jedi. And we produced a global height map at 10-meter resolution. The good thing is that although this map is global, over a small forest in France, it shows the same kind of quality than our regional map. So this is a good prospect for starting to monitor forest at scale with better accuracy. Now, to finish my presentation, I want to say a few words about very high resolution. We are talking about meter or sub-meter images from satellite or airborne data. If you take a little region in Senegal here from the MODIS data, where you see some kind of colors, you don't know what is there. If you look at Landsat data, well, you see there is some pattern, but you don't know what it is. And if you take some planet data, every day you have an image like this, you recognize clearly the different shrubs and trees and landscape elements. Another example, this is for Germany, small region, MODIS, don't see anything. Landsat, see something, and with the planet data, you can see that it is a kind of a motorway crossroad with different tree species, plantations, tall trees, and so on. So clearly, the spatial resolution is a new window to look at forest management, health, species, age. And we've been applying also deep learning to try to increase the resolution of the map. This is some work from CU Liu in Copenhagen University. We trained the deep learning model to learn how to make height from the planet data. So the planet data look like this on the top. You have the airborne LiDAR map, and you have the reconstructed map. It's not exactly the same, but it's similar. And this gave us the first 3-meter height map of forest in Europe and canopy cover. And out of that, we could look at trees outside forest, because with a 3-meter canopy cover map, you can look at everything which is trees outside forest. And we find that in the Netherlands or UK, you have more than 25% of the trees area, which is outside forest. If you look at a map of the percent of tree forest cover in the Nordic countries, are not very high, but all the Western Atlantic facade of Europe shows very high fraction of trees, which are in hedgerows, roads, gardens, cities, everything which is not a forest, and they sum up to more than 10% of the European tree cover, which is significant, at least in some countries. A lot of these trees are in urban landscape. Some of them are in cropland with agroforestry. A lot of them are in grassland because of hedgerows and landscape containing trees. You can go even further. For Denmark here, we exploited very high resolution images. We're talking about airborne images, RGB image at 20 centimeter resolution mixed with airborne LiDAR data. And we use the segmentation multitask model. So the model does a height and a crown segmentation for each tree in Denmark. So we're able to count every tree in Denmark, including those which are outside forest. This kind of data are interesting for management because if you know the density of tree in each forest, you can look at self-thinning exponents and things like that. We also use the worldview data. This paper was published in Nature, I think a year and a half ago. Segmentation, half-meter satellite data, and we counted 1 billion trees from the Atlantic Ocean to the Red Sea in this region where most of the land cover data is saying there is no tree. There are trees, of course, they don't represent a huge amount of biomass, but they're very important for human beings and rural communities. We did the same for Rwanda, using airborne images, first countings of all the trees in Rwanda. And in a recent paper published, I think last week in Nature Communication, we made the difference in the area and number of trees between 2008 and 2019. 2008 was from airborne photos and 2019 was from satellite measurements. And we observed that there was a lot of tree increase in agroforestry landscapes and also in restoring forest. This is a restored forest. You see it has very sparse trees in 2008, and the trees have started to increase a lot after only 1 decade. So for the first time, we can do, once you have the tree, you have the height. If you have allometric function at tree level, you can do basically a tree level NFI. Yeah? So you can count all the trees and how the trees change at the country level. Another recent application, India. India is the largest country for agroforestry, so it has a lot of trees in crop field, as you can see in the figure. So we made a difference for very large trees because satellites have limited resolution. So we take only the trees that have an individual crown area larger than, I think, 80 square meters. And we looked at the trees in 2010-11 and the trees in 2018-22. And all the pink dots are large trees that have disappeared, in particular in central India during 10 years. So a lot of large trees appear to have completely disappeared from agroforestry landscape in India. We collected survey data from several rural communities. We thought it was due to health, disease, or drought, but in fact, no, it's just people, you know, they grow crops and they have machines and they don't like the trees when they harvest crops. So that has led to the disappearance of 36 million trees in agroforestry in India. Last but not least, with these very high resolution images, as you can see here, there is a lot of information. You can almost see different trees, the shadows, how the trees are ordered. So we asked ourselves the question, can we predict something very difficult, the biomass of one plot? And biomass is extremely difficult to predict. Height is relatively easy, but biomass is extremely difficult. By using the texture and the high resolution property from the images. And in this model, we are going to ask a UNET model, a CNN model, to create the biomass of each plot of Denmark. So we keep half of the plot for validation, half of the plot for training. And we also ask the model to calculate the allometry because we know that the shape of the tree is not universal. And even NFI people, they use a fixed equation for different types of trees. And it leads to large errors, not speaking about wood density, of course. And we found on the right that the CNN model is able, this is cross-validation plot, huh? So it's a forest inventory plot. We did not look at the biomass, we just see how the model trained on other plot is able to capture the biomass. And you know, for a very high range, even for high biomass systems like 400 tons per hectare, the model is capable to simulate the biomass extremely well with a R-square of 0.86. And what is amazing is that it manages to find information from the very high resolution sub-meter image, which is completely hidden. If you use a segmentation, you can segment every tree and you can apply allometric equation for each tree. You can also kind of tree level based carbon inventory. You can see that the segmentation is less performant than the deep learning directly on biomass, probably because in the segmentation, you are missing understory trees, which grow under tall trees, and they contain biomass, and that's the reason why there is a tendency of the brute force segmentation models to underestimate the biomass compared to the kind of direct deep learning-based inference. So to conclude, well, we need, of course, to have a better integrated forest monitoring system. Most of the forest carbon loss occurs at small scale from mortality events or disturbances. I believe that the NFI sampling scheme is very insufficient to capture the changing regional patterns of carbon loss and even carbon gains. It's good as a sample for national budget, that's it. So we need satellite observations, we need artificial intelligence models, but in the moment, we also need ground-based data. Typically, everything I presented has to be carefully evaluated against ground-based data. So we are not yet in the stage where we don't need NFI. Maybe in 10 years, I think, yes, we can do everything with satellite and we don't need ground data, but we are still, living on a kind of world where the forest inventory data are very important. We have made huge progress with those deep learning models and the new type of satellite data, in particular spaceborne LiDAR and high resolution imagery, to do a much better job to monitor height, structure, biomass change over time. And it's probably what will give us the foundation of a monitoring system. Conclusions. There is clearly a deluge of satellite data from different sensors, lasers, commercial imagers, sentinel data. It's more than what researchers can process. The old school of remote sensing groups were trying to use physical-based retrieval models with radar equations, BRDF and so on, to try to map forest structure. But those models have limitations, and they cannot achieve the fusion of different data that we can now have access to with artificial intelligence tools. It's a bit of a sad news because you lose the understanding of the physics, but you gain in the prediction. So recent advances in deep learning have allowed us to monitor forest with a very high resolution and better accuracy than before. With very high resolution images, it's even possible to go down to tree level. And as I said in the before last slide, ground-based data still remain critical for the evaluation and sometimes the training of satellite products. Okay, I think I will stop here. I hope I haven't been too long, and I'm happy to answer any question.
Thank you very much. Thank you very much to both speakers. Thank you, Nicolas, for the exciting updates on the project. And thank you, Philippe, for the so impressive and comprehensive talk. Even though we are slightly late, I think it would be very interesting for everybody to have a chance to ask questions to the two speakers. So please, if you have any questions, raise your hand, unmute yourself, and I'll give you the floor. Any questions?
There is Albert, but he's muted maybe.
I don't know. Yes, now he's raised a hand.
And there is a question in the chat as well.
Yeah, okay, we'll deal with the chat later on. Now, please, Albert.
Yeah, you can hear me? Yes.
Yes.
Philippe, there is a large body of discussion at the moment on the inventory of the edges in France. Do you think the technique can be applied to do this inventory and the evolution?
Yeah, sure. We are working with the NFI people, and they already would like to use our maps. Yes, of course. I mean, in France, we still have some problems with high biomass forest, and when the trees are taller than 30 meters, it's very hard to see them growing in height. So we need to basically look at biomass change. And in order to monitor biomass with JEDI, you need to be able to simulate the whole waveform. And that's what we are working on using another new technique called contrastive learning or foundation models, because UNet model is not performant enough to simulate the full waveform, like the thickness of the canopy or the vertical structure of the canopy from JEDI.
Okay, I made a mistake when I say edges. I wanted to talk about edge rows. You know, in the
edge rows, yeah.
Yes,
sorry,
it's a mistake for me. Yes.
Yeah, with the planet data, you can see edge rows, at least the big ones, because you still have a limitation, which is the 3-meter resolution. So small hedge rows, you won't see them, but big hedge rows, you will see, indeed.
Okay, thank you.
Thank you. I see, I think it's Christian. Yes, Christian, you have put a question down in the chat, but please, can you speak up and ask it directly?
Yeah, I can see the question in the chat. So do you estimate the height from 3-meter imagery because you need 3D models? You have airborne LiDAR data, which are point cloud data. So they are aggregated at 1-meter scale, at 3-meter scale. And then we just match the planet image at 3-meter using a deep learning model to be able to reconstruct the height from the airborne LiDAR campaign. And it works good enough to have a continuous canopy height model at 3-meter resolution. So you don't need 3D models, basically. With the deep learning, you recognize from the features of planet, it's more than the regression. You have all this texture, this context, which are related to the images that obviously can be exploited to produce a relatively accurate 3-meter canopy height model for the entire Europe. So you don't need 3D physical models. That's a bit frustrating, I know, but basically the AI is taking you to something that you cannot interpret, but that works quite accurately.
Nicolas, please.
Yes, thank you very much, Philippe. Are there any chances? Actually, Hervé just wrote the question. Could we recognize tree species? This was my question, actually.
Yeah, we work on it. I guess it's possible if you use the temporal data, if you have the phenology, because to recognize tree species, you need phenology. We try to do it, but we are limited by the number of ground data because the NFI don't give you the coordinate of the plot. So if you cannot collocate, Sentinel-2 pixel with an NFI plot where you know the species, it is more difficult. We have tried to use some training set. We tried to use the PlantNet data, in RAS PlantNet, but we were very disappointed because PlantNet is 99% of people who go in cities and they look at flowers. But very few people with PlantNet go in forest and measure an oak. And even when they see an oak, maybe it's a 1-meter oak, it's not a 30-meter one. So using PlantNet, which is a huge data set to recognize species with satellite is going to be frustrating. So I believe it's possible, but we have to be careful because the satellites will only see the top of the canopy. So you need to know what are the dominant species. But if you have other species in the understory, I'm not that confident that we will be able to have this full species mapping in the mixed forest.
And are you already working on products such as leaf area index or things like this, or other products like this one?
Not really, because there's been a lot of work for LAI, no, we are mainly concerned by height, vertical structure, biomass, species, a bit less by biophysical indexes like LAI and things like that.
Thank you.
But species, I agree, is a very important new things to try to do.
Yeah. Is this like what is the computational need for generating such maps if it has someday to be included in monitoring web platforms such as the one?
It's very low. Typically, the model over France to generate the map, we take the image on the Google Earth engine, we pre-process them to create some mosaics and so on. Then we train the model with 1 GPU. So it's a 1 PC with 1 GPU. It takes about 5 days. And then once you have the weight of the model, to create the map is 1 hour. That's for the French map. For the global map, it's a bit heavier because we have 35 terabytes of Sentinel data as an input. It takes about 3 days with 3 GPUs to calculate the weight of the model. And then it takes about 1 week with 40 GPUs to do the global map. So a grad student in master degree was able to do the global map in about 10 days. But if you want to calculate large areas, you need to have a server with a lot of GPUs, and you can buy access or get access for free to like CNRS. They have a Janzé server where you can get access to a lot of storage and GPU. So I don't think we are limited at all by the computing time now.
Mm-hmm. Okay, so it might be something interesting at some point to add in FGIS.
Yes, absolutely.
Yes.
Okay, great. Thanks a lot for this very nice discussion. Is there any further question either in the chat. No, I don't think so, or live.
No, I think I was seeing the question of Hervé Cochard. Also, what is interesting is to look at, let's say, water stress index and things like that. Using this planet data, you have 3-level daily measurement of NDVI, and they were showing in Switzerland. They compare with the dendrometer measurements, and the daily dendrometer data were already well correlated just with the planet basic indexes. So with deep learning, probably it's possible to do a much better job to detect, drought impairment of trees using those data.
Yes, I don't want to speak instead of Hervé, but because there are two things: there are detecting and there are anticipating, and this is where models are useful, and probably the models that we develop could be constrained somehow. This was the point of my talk, to show that this model could predict something, but they need to be constrained with this structure data, such as leaf area, or but we also need the validation data to see if we can accurately predict a real water stress in a real forest at a real high resolution, and this is where we are, I think.
Yeah, thank you very much for this final comment. Right, so I think we can close the debate here if there's no further comment. Thank you very much again, Philippe, for accepting the invitation and for this truckload of food for thought for the project. Thanks a lot. Thank you, everybody, and see you soon.